In part 3 of this video series, we are going to take a look at refractory periods for neurons. Refractory periods deal with when a neuron won't and will be able to generate another action potential. To fully understand refractory periods, one really needs to know a lot about the action potential itself. So if you missed my first and second video over the action potential, I would recommend that you go watch those two videos. Those are linked on the screen as well as in the description. If you have watched those two videos and you understood them pretty well, then refractory periods, which are often seen as a relatively challenging concept, are actually not all that difficult to understand. So there are two different refractory periods. There's what's called the absolute refractory period and the relative refractory period. This graph, which I did a full analysis of in part 2 of the video series, is what we use in order to look at these two refractory periods. We will start with the absolute refractory period. Simply defining the absolute refractory period is very easy. It's the period of time in which another action potential under no circumstance can be generated by the neuron. So what we need to do is take a look at when the absolute refractory period occurs. What's the period of time in which the neuron, under no circumstance, can generate an action potential? And more importantly, why is that the case? Anything that happens between the two black lines on the graph, so I will highlight that in red. Anything that happens between those two black lines, looking at the action potential graph, that is within the absolute refractory period, the period of time under which another action potential under no circumstance can be generated. So we can use this action potential graph now to understand why that is the case. Why during this period of time between anything that happens between those two black lines, why during that period of time can another action potential not be generated? The first part of this is rather easy. So the first black line starts right here. What does right here mean? That is at negative 55 millivolts within the hillock. That's threshold. So when the hillock gets to threshold, negative 55 millivolts, what happens? Right? Voltage-gated sodium channels open up within the plasma membrane of the hillock, and sodium shoots into the hillock and drives the interior from negative 55 millivolts up to positive 30. That is exactly what we're seeing right here. That's happening between the two black lines, so it must be part of the absolute refractory period. Why that's the case, yet again, is very easy. What happens when we get to threshold, right within the hillock? An action potential happens, right? A non-decremental wave of electricity is being generated. This positive wave of positive 30 millivolts is going to travel down the entire length, ultimately, of the axon. So the point is simple. If at negative 55 millivolts, if at threshold within the hillock an action potential is generated, then of course, when an action potential is actively happening, another action potential can't possibly be generated. That wouldn't make any sense whatsoever to say that when the action potential is occurring, another action potential happens. At least in the universe that we live within, that I know of, that would be completely impossible. So that's the first part of the absolute refractory period. You can simply say, when an action potential is happening, another action potential can't possibly occur under any circumstance. The second part of the absolute refractory period starts at positive 30 millivolts, right? Peak positivity within the axon hillock. And the second half of the absolute refractory period will start at positive 30, and it will last until the hillock is repolarized to a little bit beyond or a little bit more negative than the threshold value of negative 55. So the absolute refractory period would last until the interior of the hillock was between, let's say, negative 56 and negative 70 or so. This is going to vary a little bit between neurons, which I will talk about shortly. So there's a small amount of variance between how long the absolute refractory period exists between neurons. But generally speaking, this is the second part of the absolute refractory period. From positive 30, the absolute refractory period lasts for a decent portion of repolarization until the interior repolarizes to somewhere between negative 56 and, let's say, negative 70. And at that point, the absolute refractory period would be over. So the obvious question is, why is the second half part of the absolute refractory period? Why from positive 30 to negative 56 to around negative 70 perhaps? Why is that part of the absolute refractory period? Why under no circumstance can another action potential not be generated during this period of time? And that requires one to think about what is happening at positive 30 millivolts. When the interior of the hillock hits positive 30 millivolts, two things occur. Only one of them for the moment is really relevant. The first thing that happens is the voltage-gated sodium channels close, and this is actually the relevant one. But it's how they close. At positive 30 millivolts, the voltage-gated sodium channels inactivation gates close. Right? Highlight those in red. If you remember from the other lectures, the activation gates are actually open, or they remain open. What closes at positive 30 are the inactivation gates. It's not fair to just say that the voltage-gated sodium channels close. Specifically, their inactivation gates close, and that's what prevents any more sodium from being able to come in. At the same time, the voltage-gated potassium channels open, and that allows a lot of potassium to shoot out through its chemical and also electrical driving force under this circumstance, and that begins to drive the interior back down towards negative 56. From positive 30 back down towards negative 56. Now, why am I saying negative 56? Because that's when I told you that's the soonest that the absolute refractory period could be over. So this must imply that the absolute refractory period ends whenever the voltage-gated sodium channels reset. Somewhere between negative 56 and maybe even all the way down to negative 70, depending upon the neuron, that is when these voltage-gated sodium channels are actually going to reset, meaning that their inactivation gates in red will open up and their activation gates in green will close. And once those voltage-gated sodium channels have reset, then the absolute refractory period is over and you enter into the relative refractory period. So the question is, of course, why is it that when the inactivation gates on the voltage-gated sodium channels are closed, why does that make it part of the absolute refractory period? Because as long as those inactivation gates in red on the voltage-gated sodium channels are closed, and that's going to happen between at least positive 30 and negative 56. As long as those inactivation gates stay closed, then you are within the absolute refractory period. And the answer is these inactivation gates under no circumstance will open up under a voltage. If you remember from the prior lecture, they're timed. They don't open under a voltage. that serves a benefit because as the interior repolarizes to threshold -55, they don't open again. Those inactivation gates stay closed and another action potential does not occur. That benefits the neuron. You have to get somewhere between -56 and -70 in order for them, the voltage-gated sodium channels, to reset, the inactivation gates to open. And at that point, it's possible for another action potential to occur. But as long as those inactivation gates are closed, which don't respond to a voltage, there's absolutely no way to get the voltage-gated sodium channels to open again. It's impossible. So between +30 and -56 during repolarization, the voltage-gated sodium channels are shut in such a way, meaning their inactivation gates are closed, that there's nothing that will get them to open again. You can't just depolarize the interior back to some level and get these channels to open again. It just can't be done because those inactivation gates won't open under a voltage. They have to reset first, meaning they have to open again, the inactivation gates, in order for it to even be remotely possible for another action potential to occur. So this is the state that the voltage-gated sodium channels would be in from +30 to at least -56. And beyond that in some neurons, even more negative. You can see, right, the inactivation gate is closed. And if the inactivation gate is closed, then these voltage-gated sodium channels within the membrane of the hillock cannot open again. And if they can't open again, you can't get another action potential. The only way that you get an action potential within the hillock is if the voltage-gated sodium channels open, and that allows sodium to come in and drives the interior up to +30 millivolts, which then can propagate down the length of the axon. As long as these inactivation gates are shut, these aren't opening again. You're not getting another action potential. You need for the voltage-gated sodium channels to reset and look like this. You need for the inactivation gate to open, and you need for the activation gate to close, and this will happen between -56 and -70. And once we're back to this orientation, then if we can get the membrane potential back to threshold, then the voltage-gated sodium channels will open again, and we will, in fact, get another action potential. So let's briefly recap and then move on to the relative refractory period. The absolute refractory period exists between the two black lines. So from by the time the hillock gets to threshold and an action potential is generated, right, voltage-gated sodium channels open up, sodium shoots into the hillock, drives the interior up to +30. This is part of the absolute refractory period. From threshold to +30. An action potential is actively happening. Of course, you're not going to get another action potential. All right. And then from +30 all the way back down to somewhere between -56 and -70 is the second half of the absolute refractory period. And another action potential cannot happen under any circumstance during this second half here of the absolute refractory period because the voltage-gated sodium channels have their inactivation gates closed. Throughout this entire range, that is true. And as long as those inactivation gates are shut, no voltage will cause them to open again, and thus they will not open, and you cannot, under any circumstance, get another action potential. But once they have reset, and that's going to happen somewhere here, now you've entered into what is referred to as the relative refractory period. Once those voltage-gated sodium channels have reset to their original orientation, now you've entered into a separate portion or a separate refractory period called the relative refractory period. The relative refractory period is also very easy to define. It is the period of time in which another action potential can occur, but it is harder than normal to get the neuron to generate that action potential. So the relative refractory period occurs between the two black lines. It occurs or starts once the voltage-gated sodium channels have reset. Once the inactivation gates have opened and the activation gates have closed, that varies a little bit, as I've said, could be somewhere between negative 56 and negative 70. That's the point in time in which the relative refractory period starts. At that point, you can get another action potential to occur within the neuron, but it's harder than normal. So it lasts throughout hyperpolarization and then back up to the resting membrane potential. Once you return to the resting membrane potential of negative 70 from hyperpolarization, so you get down to negative 75 or so, and then by the time that you depolarize back up to the resting membrane potential of negative 70, that is the end of the relative refractory period. So the beginning of the relative refractory period is when the voltage-gated sodium channels reset, and the end of the relative refractory period is once the interior has returned to the resting membrane potential, again, between the two black lines. That is where the relative refractory period exists. So now let's explain why this is the relative refractory period. Why can another action potential be generated, but it's harder? So yet again, you have to think about what is occurring within the hillock. Let's just pick a value and say negative 60. In this neuron, that is when the voltage-gated sodium channels have reset. Okay? In black, those are the voltage-gated sodium channels, and they've reset. Their inactivation gates are open, and their activation gates in green are closed. This means that if you can depolarize the neuron, the hillock region, back to threshold, these voltage-gated sodium channels will open again, and you'll get another action potential. But why right now is it harder to generate an action potential than it normally would be? And the answer is quite simple, because the voltage-gated potassium channels are open. The voltage-gated potassium channels are actively open right now, and what's happening? Potassium is shooting out, driving the interior more and more negative, right? Potassium is actively leaving through these voltage-gated potassium channels, and its leak channels too, and that is repolarizing the neuron. It's actually the hillock region, right? It's going to actually repolarize it beyond the resting membrane potential of negative 70, the resting membrane potential value of negative 70, and it's going to hyperpolarize it all the way down to negative 75. So these voltage-gated potassium channels being open, that's one of the reasons why during the relative refractory period, another action potential can be generated, but it's harder. Let me explain. So if we wanted to get the hillock region to threshold, we'd have to get the interior to negative 55 millivolts, and that then would cause the voltage-gated sodium channels to open again. So it's feasible. Like, another action potential could happen right now. If we can depolarize the hillock region to threshold, then an action potential will in fact happen. But as I've said, we're in the relative refractory period right now, so it's technically harder than normal. But why? Well, let's pretend that a whole bunch of graded potentials from the dendritic regions are headed towards the hillock region right now, right? They're made up largely of sodium ions, these waves of positivity, right? They're headed towards the hillock region, and they're trying to depolarize the hillock region to the threshold. Basically, we're trying to get enough sodium into the hillock region to drive it from negative 60, negative 65, negative 70, whatever it might be during this period of repolarization. We're trying to drive it back towards negative 55. That's very difficult to do right now because the interior is actively becoming more negative, right? These voltage-gated potassium channels are open right now, And that means that potassium is actively shooting out of the hillock region and actively making the interior more negative. Right? The extra potassium leaving right now is repolarizing the neuron. It's actively trying to make the hillock region more negative. And then you're trying to get sodium from the dendritic regions, which are causing those depolarizations and graded potentials. You're trying to get sodium into the hillock region to get the hillock region to threshold. But that means that the sodium has to actually overcome the fact that potassium is leaving the hillock region at a greater rate right now and making the interior more negative. So this makes it much harder to actually get the hillock region to threshold than it normally would be. Because under a normal circumstance, these voltage-gated potassium channels wouldn't be open, and there wouldn't be all this extra potassium leaving, right? Potassium wouldn't be leaving at as great of a rate. So by consequence, under a normal circumstance, the interior of the hillock isn't actively becoming more negative as we're trying to get the hillock to depolarize and get to threshold. So this is the first explanation as to why this portion of repolarization is part of the relative refractory period. Another action potential can happen right now, technically, if we can depolarize the interior of the hillock to negative 55, that'll cause the voltage-gated sodium channels to open, but it's much harder to get the hillock to threshold and thus generate an action potential right now. Because the voltage-gated potassium channels are open, potassium's shooting out, actively making the interior of the hillock more negative as we speak, and then we're trying to depolarize the hillock. That's very hard to do. It can be done, but it would require the presynaptic neuron to release a lot more excitatory neurotransmitters than it typically would, to allow a lot of extra sodium to come in, to get that extra sodium into the hillock region to overcome the fact that potassium is actively leaving, making the interior more negative. That extra sodium then could overcome the extra potassium that's leaving and theoretically drive the interior back to threshold. But no matter how you look at it, this period of time, it's much harder to get to threshold than it normally would be. And it's because of these voltage-gated potassium channels being open. But that can't possibly be the whole story, because the relative refractory period lasts from when the voltage-gated sodium channels reset all the way through hyperpolarization and then back to the resting membrane potential, so that slight period of depolarization that occurs. Right? That's the entire relative refractory period. And what I'm saying is, the voltage-gated potassium channels closing puts an end to hyperpolarization. That's when the interior begins to depolarize back towards the resting membrane potential. So the voltage-gated potassium channels are eventually going to shut. And even after the voltage-gated potassium channels shut, the relative refractory period continues on. So simply saying the voltage-gated potassium channels being open is what causes the relative refractory period to occur would not be accurate. This is why I like to split the relative refractory period up into two parts, even though that's not technically accurate, or not technically the way that it's spoken about. The relative refractory period, I like to say the first part is between when the voltage-gated sodium channels reset and then when the voltage-gated potassium channels close. That would be everything within here. Okay? That part, again, easy to explain. If the voltage-gated potassium channels are open, potassium's actively shooting out, actively making the interior more negative. Thus, it's a lot harder to get the interior to become more positive and get to threshold and have another action potential. But what about once the voltage-gated potassium channels have shut? How is that still part of the relative refractory period? Meaning, from the end of hyperpolarization back to the resting membrane potential. Or we could say, maybe a little bit more accurately, from peak hyperpolarization of negative 75 back to the resting membrane potential of negative 70. So when this depolarization period happens between negative 75 and negative 70. How is that part of the relative refractory period? Again, the period of time in which another action potential can occur within the hillock, but it's a lot harder. The answer to that is also quite easy. So pretend the interior is at negative 75 millivolts. Okay. We're not going to talk about why the interior begins to depolarize back towards negative 70 right now. That is in the last video. Very confusing concept, takes time to get through. But that is what's happening right now during this, what we'll call second half of the relative refractory period, even though it's not really a thing. We're moving from negative 75 back towards negative 70, back towards the resting membrane potential. Why is this part of the relative refractory period? Again, easy to explain, because if the interior is at negative 75 and these graded potentials from the dendritic regions, which are largely made up of sodium, right, they're headed towards the hillock region. And inside of the hillock region right now, it's negative 75 millivolts, or negative 74, negative 73, or whatever it is as you move back towards negative 70, as you depolarize towards negative 70. What usually has to happen is, under a normal circumstance, you only have to depolarize from negative 70 to negative 55 millivolts. That would bring the interior of the hillock to threshold. Right now, you need to depolarize the hillock from negative 75 to negative 55. That is an extra 5 millivolts of voltage. The hillock region is hyperpolarized, right? It's more negative than the resting membrane potential. So thus, it's harder, logically, it's harder to depolarize a region by 20 millivolts than it is to depolarize a region by 15 millivolts. Usually, you only have to depolarize the hillock from negative 70 to negative 55 to get to threshold and generate an action potential. That's only 15 millivolts. But right now, during this portion of the relative refractory period, you have to depolarize the hillock from negative 75 to negative 55. That's 20 millivolts rather than 15. That requires more sodium, right, to be able to get into the hillock region in order to be able to accomplish that. That requires more significant or more frequent graded potentials, essentially, is the accurate way of saying that. Meaning it's harder, right, to get the hillock region to threshold than it normally is. And that is why this region, or this portion, is part of the relative refractory period. So from peak hyperpolarization, negative 75, until we get back to the resting membrane potential of negative 70 millivolts, this is part of the relative refractory period. Another action potential can be generated, but it's harder than normal. And you can look at this graph and easily see why that is the case. Usually, we only need to depolarize the hillock from negative 70 to negative 55 millivolts. That doesn't take as much sodium or graded potentials as getting the hillock from negative 75 to negative 55 millivolts. It's harder to depolarize the hillock region during this period of the relative refractory period simply because of the fact that the interior is more negative or hyperpolarized. And that's going to be true for any part of this, right? Even if it's at negative 71, during the relative refractory period. Even if it's at negative 71, which would happen somewhere in here, you still need to depolarize the hillock region by 16 millivolts rather than the usual 15, which is harder, right? Requires more graded potentials and more sodium. So that is the relative refractory period. It is from the time the voltage-gated sodium channels reset throughout hyperpolarization back to the resting membrane potential. The first half of it, largely due to the fact that the voltage-gated potassium channels are open. The second half of it is simply due to the fact that the interior is more negative than it normally would be. The interior of the hillock is hyperpolarized. And that concludes part 3 of this video series. The next part of this lecture series, which a link will pop up on the screen shortly, as well as a link within the description, that lecture is going to take a look at how myelin sheath existing on the axon of a neuron allows for that neuron to conduct action potentials at faster velocities. It's a concept known as saltatory conduction. As always, if you have specific content requests, you can always send those to me as well.